Buildings look like static objects, but they are really machines. They have moving parts. They have heating and ventilation equipment. They have elevators. They have stairways. And they have lots of energy. And that energy, when released, has the real potential to invite disaster.
Since the dawn of civilization, humankind has sought to proclaim its unique intelligence and mastery of its environment by creating buildings. The human mind could transform wood and stone into structures that provided more than shelter from the elements. Humans hoped to create buildings that would represent them to the ages and become symbols of their achievements. But often these symbols lacked a durability that matched the vision that created them. Since the first mud bricks were stacked to form a wall, humans have struggled to erect buildings that would stay up. The 7 wonders of the ancient world were created to represent the skill and power of the societies that built them. But all these ancient wonders have fallen to vandals or natural forces, all save one. The pyramids at Giza were constructed over 4,000 years ago to proclaim the greatness of 3 Old Kingdom pharaohs. While the Hanging Gardens of Babylon and the Colossus of Rhodes have become dust, the pyramids remain. Their architect wisely placed them on solid bedrock. The Pyramid of Khufu alone contains 6.5 million tons of stone that still stand in almost perfect alignment. But even Egypt's master builders made mistakes.
If you look at the Pyramid of Khufu, the Great Pyramid, the one that we're all familiar with, you think nothing could ever bring down that man-made mountain. But not too far from that Great Pyramid is a lesson called the Pyramid of Midim. And that pyramid did encounter the unexpected.
The architects of Midim forgot that the above-ground mass was meaningless unless well supported below ground. The pyramid at Midim no longer looks like a pyramid. It was so poorly built that it could not support the casing stones that once lined its surface and now lie crumbled at its base. All that remains is the pyramid's inner core.
They kept pushing the envelope as time went on. And when Midim was built, it was built on sand, and sands, shift over time. So as the sands began to move, these stones began to shift away from the center, and many of them fell over.
Not even the passage of centuries cured human forgetfulness about the importance of foundations. Aesthetics in a building are meaningless unless they are combined with sound engineering. In the 12th century, towers in Italian towns and cities expressed a civic pride and demonstrated to their world the town's wealth and accomplishment. Each town's efforts grew more and more elaborate as they built higher and higher in a race to create the most impressive towers. In 1174, the leaders of the Italian city of Pisa decided to add to the beauty of their town by building a bell tower of their own.
The fact is that people didn't know that much about foundation construction, and so the Pisa Tower was built on a clay type of foundation that tends to compress over time because it's near the water, so that when the water is squeezed out of the clay, it tends to sink. And in that particular case, it tended to sink unequally.
Almost immediately, the tower began to tilt, and as the centuries have passed, it has leaned 15 feet out of alignment. But it could have been worse.
Pisa is a tower that stands due to circumstance, and the circumstance was the builders at Pisa could not proceed on the original construction schedule. They had to hold up twice. In fact, the whole construction of the tower took over 200 years. The reason that was fortuitous was it gave the weak ground time to find an equilibrium underneath that tower of Pisa. Had they built on a fast track, like we like to build our buildings today, experts think the Leaning Tower of Pisa would not be a tower at all. It would be rubble on the ground.
Thousands come every year to see the famous Leaning Tower. The tilt has been virtually stopped by adding a network of cables to counteract the pull of gravity and pull the tower back toward vertical. After over 800 years, Pisa's beautiful tower has managed to survive its builders' mistakes. But not all defects in the construction of a building show up as quickly as they did at Pisa. In another Renaissance bell tower, the structural flaws remained hidden for centuries. No one who visits Venice is likely to forget the graceful campanile that soars over the piazza of San Marco. But few visitors here realize the building that so enchants them is not original. Poor construction or a shift in its foundation almost robbed Venice of its lovely tower.
In 1902, the original bell tower, over 800 years old, fell in. The good story, there were no casualties. The only loss was the caretaker's cat.
Some people, especially romantic Italians, attribute it to old age. It simply got too old and it came down. I think it's more likely that it was built in Venice. Venice, as we know, is built on islands that are actually sinking over time, and it's very possible that the foundation again began to fail.
Some have noted that the original structure may have been weakened during remodeling. Others have cited lightning strikes, and still others feel centuries of clanging bells weakened the tower until it collapsed. But for Venetians, it is only important that, original or not, the wonderful tower remains as the most famous landmark of their city.
With the passage of time, eventually, many of us will never know whether it was original or whether it was a recreation. And it really won't matter, because buildings are not like people. They can have a second life, they can have a third life.
Renaissance bell towers were not the only structures where sound building techniques were threatened by the urge to impress one's neighbors. In medieval Europe, some local bishops or cardinals set out to build churches on a scale that was more grand and impressive than those built by their colleagues. In 1247, the bishop of a small town in France set out to build the grandest of them all.
The bishop near Beauvais, France, got into a disagreement with the king, with the royalty of France. And his expression of competing, of trying to exceed the power of the crown was to put up the grandest of the Gothic cathedrals.
The vaulted ceiling that soared 150 feet over the choir hinted at a finished church that would rival St. Peter's in Rome in style and scale. But the support for the great weight of the vaults was poorly conceived and executed. In November 1284, the enormous structure collapsed. In 1564, another attempt was made to erect the complete cathedral, but this also collapsed. Over the centuries, the great church has been partially rebuilt with added structural support. But the great nave of the cathedral was never finished. What remains in Beauvais is a testament to determination, as well as an example of flawed architectural planning.
The understanding of the science behind buildings really did not occur until the, let's say, late 17th, early 18th centuries. And since then, and it's been evolving since then, now we have science behind us. We are able to make calculations. And because of computers, we can make very elaborate calculations. That's why our buildings today are so much lighter than they were even 100 years ago.
But technological advances and contemporary scientific calculation cannot make up for what causes so many failures in the buildings we create. Even in modern times, it is often simple human error that continues to invite disaster.
Those of us who go into buildings hope that engineers really know what they're doing, that they meet the highest standards of foresight and thoroughness. They put that extra measure of devotion in, not just to the building, but to the people who will use it. This
tower is seen the world over as a graceful expression of design. Its height and the complexity of its interlaced wrought iron components required an engineer of imagination and, equally as important, obsession with detail. Gustave Eiffel was such a talent.
Such a thorough engineer with his thousands of drawings that out of thousands of structural members that went into the tower, they all fit. To me, the Eiffel Tower stands in sharp contrast to a project such as the Hartford Civic Center Coliseum.
In 1970, the city of Hartford, Connecticut decided to build a civic center. Architects and engineers came up with a unique roof design of linked pyramids that would cover almost 2.5 acres. But even before the unique roof was lifted into place, observers began to notice that, unlike the Eiffel Tower, the pieces in this building didn't fit.
Contractors complained that they were not able to assemble the structure very easily because the bolts would not fit through the holes. Passers-by, not casual passers-by, but architects or engineers noticed that the roof seemed to sag under its own load quite a bit. And yet nobody listened.
We should know now that's a problem. If bolt holes don't line up, it's time to take a break. Bring in the experts and see whether or not that's a severe problem.
It was a severe problem. On the night of January 18th, 1978, as fans watched a basketball game in the Civic Center, a heavy snow fell outside. Later that night, the snow-covered 1,400-ton roof collapsed in a mighty roar. Had it failed 6 hours earlier, it would have fallen on 5,000 people. The pyramid grid of the roof on the Hartford Civic Center bent under stress in ways never considered in the design. But the most disturbing factor was that so many warnings had been given and ignored. The Civic Center had fallen because of the failure of hundreds of structural parts. But some disasters offer few hints of their approach and come about because of only one piece of a huge structure. In 1928, the Silver Bridge was completed, connecting the town of Point Pleasant, West Virginia, with Gallipolis, Ohio, across the Ohio River. As it opened for traffic, the bridge was considered a marvel of engineering. Instead of being suspended by cables, the span depended on 50-foot rods that were joined by flat steel plates held together with large metal pins. It was as if the bridge was held up by massive bicycle chains. On December 15th, 1967, the bridge was crowded with rush-hour cars. At 5:15 in the afternoon, the 1,400-foot bridge that had been hailed as a marvel collapsed. 31 cars fell into the Ohio River. Research would show that the failure of only one plate in only one of the chain's links caused 46 people to lose their lives. But there was good to come out of this tragedy. The Silver Bridge caused President Lyndon Johnson to order an inquiry into bridge safety throughout the nation. More than 7,000 bridges have been inspected and repaired in a process that is still underway. No matter how big the structure, the smallest of parts can cause terrible disasters. Friday, July 17th, 1981. 1,600 people gathered for a dance in the atrium of the Hyatt Regency Hotel in Kansas City. None of them guessed they would be part of the worst structural disaster in U.S. history. 3 suspended walkways crossed the 120-foot wide atrium. The original plans called for the walkways to hang from individual rods running from floor to ceiling.
Instead of that, the contractor substituted separate rods between the roof and the top level and the next level down. And the designer, or one of his people, unfortunately, one of his younger engineers, approved the change. It was an improper change.
The design changes were signed as reviewed and approved by the supervising engineers, but the plans went into construction untested. Substituting 2 rods for 1 put more weight on each of the transverse beams holding the 4th floor walkway. As the crowd packed onto the walkways, they danced to the music. In a moment, the party became a nightmare. 2 of the steel-framed walkways crashed down on the crowd below. 114 people died, and 200 were injured, many maimed for life. Designers had failed to plan for the unexpected. They had added no redundancy to the structure of the Hyatt Regency walkways. When faced with a crisis, the walkways could not handle the unexpected.
What they should do is think skeptically, this is a fairly large structure that can hold a lot of people. Is my design able to take it? Can it take anything that time can throw at it?
Unfortunately, time can throw a great many things at buildings, especially when our buildings grow to become symbols of the society that builds them.
We think of a big building as holding certain things. It holds people, it holds furniture, lots of paperwork. But in fact, a tall building holds something else, a tremendous amount of energy that is really captured. It is caged inside that structure from the early days of its construction, when cranes used lots of power to raise thousands of tons high into the air. And that energy was just waiting for a trigger to be released.
Throughout history, buildings had been limited by how high one stone could be stacked on top of another. The endurance of the buildings was dependent only on natural materials to make them strong and prevent their collapse. But by the end of the 19th century, human skill and imagination were ready to create a whole new class of buildings that grew up as well as out. It was a change that would require new margins of safety and even greater concern for the unexpected. These buildings would find strength and stability not in rock and brick and mortar, but in steel. The invention of the Bessemer process made it possible to create steel that was not only stronger than anything that had preceded it, but could be produced cheaply in a diversity of lengths and shapes. But it also took another invention by a mechanic from Yonkers, New York, to at last allow buildings to grow skyward. In 1854, Elisha Otis had demonstrated safety brakes that could effectively prevent elevator accidents.
With time, the combination of the Otis elevator and improvements in electric motors made possible the high-speed safety elevator that was so smoothly running, people could feel they were in a little room rather than suspended over a hole hundreds of feet deep.
The first buildings deserving of the name skyscraper appeared in Chicago in the last decades of the 19th century. The disastrous Chicago fire of 1871 created a huge demand for new buildings. In 1884, William LeBaron Jenney met that demand when he used steel to erect what is arguably the first skyscraper, the 10-story Home Insurance Building. In 1891, Louis Sullivan, a student of LeBaron Jenney, created the sleek Wainwright Building. And in 1895, Daniel Burnham filled the facade of the 15-story Reliance Building with large windows never before seen. Only steel would allow such large openings in the walls. As the new century began, New York was also growing upward. In 1903, the intersection of 23rd Street and Broadway saw the rise of one of America's most popular and photographed structures, the 20-story Flatiron Building. City dwellers had never seen anything like it. The winds that swirled around the daring new structure kept New Yorkers holding onto their hats. In 1913, New York grabbed the title of City of Skyscrapers with the construction of the remarkable Woolworth Building. This masterpiece of Gothic glory soared to the unimaginable height of 792 feet. In 1930, the 70-story Chrysler Building became the tallest structure. But within a year, it gave up the title to the most celebrated skyscraper of all, rising less than a mile away. Completed in only a year and a half, the Empire State Building was hailed as the 8th wonder of the world. It had been only 40 years since Jenney's first 10-story skyscraper. Now, at 102 stories, the new landmark dwarfed all others. The skyscraper brought a whole new design challenge for engineers. In spite of their enormous height and size, the greatest problem in constructing tall buildings is not their huge weight, It is the great force of the wind pressing on their sides. Like all tall buildings of its generation, the Empire State Building combated the force of the wind by relying on a forest of steel columns to support it. Interior spaces were filled with these columns, restricting the size of offices and forcing people to work and walk around them. But the construction of very tall buildings brought other unexpected dangers, never before imagined by engineers. In 1945, a B-25 bomber, lost in the fog, crashed into the 79th floor of the Empire State Building. 14 people were killed, and a new threat to the world's high buildings had been revealed. For all its glory, the Empire State Building would mark a pause in American business's fascination with skyscrapers. It was not until the 1960s that prosperity revived interest in very tall buildings. New York's Rockefeller Center had been a highly successful innovation for using several tall buildings as a magnet to attract business. In the 1960s, the Port Authority of New York and New Jersey set about to use Rockefeller Center as a model to create a similar complex. A neighborhood of old buildings and small businesses in Lower Manhattan would be demolished to make way.
The plan was to build a center in Lower Manhattan that would attract, that would be a magnet for world financial trading companies, and they would call
office floors be unencumbered by interior columns. It was necessary to get the weight onto the outside wall of the building.
A column-free space affords almost any tenant to lay out the floor in the way that is appropriate for their usage. So it's not just something, I mean, it's something that is commonplace now. Almost all buildings that we design of any scale now, the goal is to make the floor plates as column-free as possible.
To deal with the problem, Robertson created a unique design. Instead of beams and columns filling the working spaces of the building, he would create the world's tallest building based on a tube.
A tube is a tremendously strong shape. It can take large vertical loads. It can take large lateral forces in the force of wind or earthquakes. And so it's a tremendous thing. And it puts all the material all the way out on the skin. Just like if you want to be stable, you spread your legs out and you're much more stable.
The outside of the tube would be a wall of columns tied to an inner core of strong steel shafts. The solution to getting the outer wall to carry the enormous vertical load was to keep the vertical columns very closely spaced. This suited Yamasaki's belief that most people would not be comfortable standing next to large windows 1,000 feet off the ground.
Yamasaki was a very, very complex guy, brilliant. He basically relied on other people's judgments. What he did want was a system where you could put your hands on something solid on each side of the windows. That was fundamental to his design.
The forest of columns was now on the outside of the building, not on the inside. Even someone afraid of heights could stand next to these windows and have no fear of falling. To connect the outer and inner load-bearing columns, Robertson chose another innovative solution. Instead of huge I-beams to hold up the floors, he designed triangular-shaped bar trusses. These were inexpensive, lightweight, and more than capable of supporting the weight. Work began in the summer of 1966. 1.2 million cubic yards of dirt were excavated to make way for the giant buildings. The 200,000 tons of steel in the Twin Towers went up quickly, considering the enormity of the task. The outer columns were put up in modules 10 feet wide, each weighing 22 tons. The 220 stories of both buildings could house 50,000 workers behind 43,000 windows. Workers would be cooled by air conditioners that could serve a city of 15,000 homes. And incredibly, every tenant was provided with workspaces 60 feet wide without a column in sight. As the last steel was set, Tower 1 topped out at 1,368 feet. Tower 2 was 6 feet shorter. When the World Trade Center towers were at last dedicated in 1973, they were indeed the tallest buildings in the world.
It required a new approach to architecture and to engineering, not just the structure part, but the rest of the building as well. So the remarkable part, I think, was the fact that a group of young, energetic folks got together and produced a new kind of building.
Robertson and Yamasaki and all the others could not know it, but 28 years after their triumph, their new kind of building would endure a new kind of terror.
One of the things engineers stay up at night about is the problem of progressive collapse. The house of cards problem, we might call it, where one piece falls away and takes down other pieces above it and below it.
In the early morning of May 16th, 1968, a woman awoke in her apartment in the Ronan Point Towers, east of London, England. She put a kettle on the stove to make tea. As she lit a match, she did not smell the gas that had filled her apartment.
What should have been a very minor gas explosion near a stove blew out concrete walls and destabilized a whole vertical row of apartments, causing a collapse all the way down to the ground.
The building had been so poorly designed that the failure of one wall had taken out the floor above, which collapsed the floor above that until all 22 floors came down. Amazingly, only 4 people died.
The future holds a lot of unknowns. What we want are structures with redundancy, with a factor of safety, to take the major assault, which might be a gas explosion, as in the case of Ronan Point, or it might be an aircraft impact.
Tuesday, September 11th, 2001, 8:47 a.m. The Twin Towers of the World Trade Center stand waiting this morning for the men and women who work in them to begin their day. Already, some 15,000 people are in the buildings. Some 35,000 will normally be working by midday. They had lost their status as the tallest buildings in the world years before. But as they stand now in the morning sun, they remain 2 of the mightiest structures humans have ever built. But even such massive buildings are not designed for what happens next. Brian Clark had just arrived at his job at a currency trading company on the 84th floor of the South Tower.
All of a sudden, there was this loud boom. Then there was this sort of glare, and I spun around behind me, and right outside the windows on the 84th floor, filling the airspace, was swirling, flaming gasoline. There were flames right there. I didn't know what it was.
What it was a Boeing 767 airliner filled with 10,000 gallons of fuel. The American Airlines plane had slammed into the 96th floor of the North Tower, killing 92 people on board and setting off a huge explosion. Stairways in the central column were wrecked, cutting off escape for those above the impact. The mighty tower struggles to handle the blow. 100,000 tons of steel is racked by the great force of the plane.
After the airplane hit the building, there was a shock wave that went up and down the tower, and the building probably moved over on the order of like 18 inches due to this initial impulse.
The tower has sustained massive structural damage. If the load resting above the impact cannot be held up, a progressive collapse similar to the Ronan Point apartments will bring the building crashing down.
I think if you had told anyone before 9/11 that you were going to take a building and remove as much of the primary structure from it, I think you'd be hard-pressed to find an engineer who wouldn't think that the building would be severely impaired and unlikely to survive that kind of event.
Like a prize fighter staggered by a hard blow, the building struggles to stay upright.
Buildings was fairly robust to be able to take this huge hit and this huge wound and not collapse immediately. And I'd have to say, most tall building designers, myself included, were not overly sure that the building would have survived the initial impact.
But the North Tower continues to stand. Remarkably, the tremendous weight of the stories above the impact is redistributed to other remaining beams and columns. There will be as yet no repeat of Ronan Point. Thousands of people begin to exit the building.
So when the plane went through one face and actually tore out, more than half of a face, instead of the building immediately collapsing, which clearly it could have done had it not been for the fact that all these elements were tied together, that was a wonderful example of redundancy and an alternate load path.
Because of the way in which the World Trade Center was designed, it gave it the unique ability to bridge over this very large kind of gaping wound, and it allowed it to do that for a significant period of time. Time that allowed for everyone below the impact zone to be able to exit the building.
As workers in Tower 1 struggle to get out, those watching the burning building look on in horror as a second plane heads for the South Tower. United Flight 175, with 65 passengers, rips through the building. Like its neighbor, the tremendous blow rocks the tower.
And the building moved. And it went, and it went, and it went, and it seemed like forever. I'm guessing, but it felt like 10 seconds. It went more, and I thought at that moment, we're going over. Those were the 10 seconds I was terrified that day.
Like Tower 1, the ability of the South Tower to transfer the load keeps the building upright. But a new threat confronts both towers. The force of the planes had knocked fireproofing off critical beams and trusses. Now, thousands of gallons of jet fuel are turning floors into raging infernos.
Each floor of this building is approximately an acre, okay? So you had 4 or 5 acres of building on fire at one time. You also had all of the conventional firefighting systems, such as sprinklers, were undoubtedly taken out by the impact.
The fire starts, it feeds on paperwork in the buildings, becomes so intense, it melts aluminum. And without the need to actually melt the steel structure, it's enough that those fires, after many minutes, cause the steel to soften.
Because redundant support had been planned into them, the towers of the World Trade Center had withstood violent blows that could have toppled them. But fires of such breadth and intensity had never been imagined by the engineers.
The building had a series of hat trusses at the top of the building, and these hat trusses, like the hat on top of your head, linked the core columns to the perimeter columns. So as the core columns or the perimeter columns started to lose strength, they would shed load to the other columns, okay? And those columns would take more and more load. More and more columns would probably fail at some point, either through loss of support, as the core trusses might have collapsed if they did, or just due to fire to the columns themselves. So the load would go to the neighbor, to the neighbor, to the neighbor. Eventually, the whole system was overwhelmed and went down together.
We may never know the exact architecture of failure. The towers had avoided falling from the plane's impact. But now, the tremendous heat of the fires brings on the progressive collapse the buildings had so far avoided. An hour and 25 minutes after it was struck, the South Tower comes down. 23 minutes after the collapse of the South Tower, the North Tower also falls.
Center buildings, each a quarter-mile high, were very special, irreplaceable. But we shouldn't forget that there are many other tall buildings in the United States, 469 buildings over 500 feet tall. In the event of an emergency, any one of those buildings will put the occupants, particularly those on the top floors, in a very desperate situation. From now on, people need to know, they need to react, they need to listen. They just can't wait for someone else's advice. They've got to know what to do right away.
Over 2,800 people had been buried amidst the twisted pile of rubble that had once been the mightiest buildings in the world. The wreckage was still smoldering when criticism began to be leveled at the engineering that had planned the great buildings. The Boeing 767 flown by the terrorists was much larger than the 707 airliner planned for in the 1960s. The design team also anticipated a plane hitting the building by accident and not design.
The big difference is the amount of fuel. The 707 we envisioned was one lost in the fog, throttles back, trying to find JFK instead of the throttle down. So the energy of impact of the aircraft was very much larger than was the design criteria.
The painful reality of what happened on 9/11 has not lessened interest in tall buildings. From Hong Kong to Barcelona, over 4,000 buildings of over 12 stories are currently being built. Each will present problems of protection and safety to the people who use them. Each will need to study the lessons that must be learned from the World Trade Center. Perhaps the most critical area to be looked into is evacuation. The stairways in the Twin Towers allowed many people to escape from a very dangerous situation. But the World Trade Center was barely half full on that morning. If the attack had happened a few hours later, another 20,000 people would have been trying to get out. To evacuate fully occupied buildings could have taken well over 3 hours. Too long in this case. Builders must change their attitude about what can be expected of our escape systems.
Architects and engineers, when they're considering tall buildings, will have to re-examine the assumptions they've made in the past. The most basic assumption they've made in the past is that you don't have to evacuate a high-rise building totally. We now know that that's a bad assumption.
Planners also need to rethink how to get firemen to the source of the fire in tall buildings.
One of the hopes that we carry with us is that firefighters will always be able to come and get us out of danger. But high floors in a skyscraper are a very remote place when it comes to firefighters getting up to help you.
Another lesson may be found in the way the stairways are designed. Although thousands of people in the Twin Towers owe their lives to those stairs, major concerns presented themselves. As in most tall buildings, the stairs in the World Trade Center had been grouped around the central core. Using this design, stairs would receive the structural protection of the steel surrounding the elevator shafts. But when the terrorist-guided planes burst through the towers, most stairways were destroyed. Future designs may change stair placement. There are many lessons from the World Trade Center which will impact how future tall buildings are designed. But one thing seems certain to engineers and architects. We cannot create designs that anticipate a particular terrorist-guided aircraft.
We do not design buildings for the impact of planes, then or even now. There will be bigger and faster planes, and if we were to design for it, the building will be uninhabitable. One wouldn't want to live or work in a building like that. It will be a bunker.
Tall buildings will continue to be built. These amazing technical accomplishments represent a practical solution to problems of how people live and work. In spite of the events of September 11th, it is important that we remember that in an ongoing world of skyscrapers, these amazing structures remain very safe.
Tall buildings are very, very safe. I mean, I live and work in a very tall building. And I would tell everybody that they're the safest buildings around.
From a structural point of view, as far as I'm concerned, high-rise buildings are perfectly safe. There's no reason for them to present a danger to their occupants in any way. So, yes, they are safe.
But those who choose to hate used two symbols of America to send their terrible message. The World Trade Center towers fought and lost a fight to stay erect. And innocent people were the victims of hatred and terror.
People ask me how I felt about it. I have to tell you, I spent a huge amount of my lifetime working on the design of the World Trade Center. It was an extremely important project to me personally, but it's a building. The loss of the building was important, but the only thing that was on my mind then and now is the fact that people lost their lives. Buildings can be replaced, hopefully with better ones, but there's no way to bring back people who are lost.
We will learn from the experience of September 11th. Buildings will become safer and more secure as architects and engineers work to plan for the unexpected. But along the way, we will never forget those who perished as two magnificent buildings struggled in vain to avoid disaster.